Imagine, just for a moment, that you are entirely weightless.
Right. Like you aren't floating in the air and you aren't falling.
Yeah, exactly. You are just suspended in this endless, immersive universe of emerald and indigo. There is no ground beneath your feet.
And there's no sky above your head. There's only the vast, enveloping expanse of the ocean all around you.
And you don't have eyes that can see sharp shapes or like distinct colors, but you can feel the light.
Yeah, you feel that golden warmth of sunlight filtering down from somewhere way, way far above.
Right. Just scattering through millions of floating, glittering particles in the water.
And you feel the rhythm of the world around you, too. I mean, you don't have ears to hear the crashing of waves on some distant shore, but your entire body senses the deep, silent pull of the changing tides.
It's like the water isn't just something you swim through. It is something you are a part of.
Exactly. You can feel the gentle tug of the currents wrapping around you, carrying you forward. You don't fight the ocean. You just, you surrender to it.
You surrender. You drift. But you aren't perfectly still either. Deep within your center, there is this silent, steady rhythm.
A slow, graceful expansion.
Yeah.
And then a soft contraction.
Yeah. It's like a heartbeat, but you have no heart.
Yeah.
You're pulsing. You're a living umbrella of glass, pushing gently against the water.
And as the day turns into night, the emerald water fades into just pitch black. But you are not alone.
No. You sense glowing bodies in the dark. Tiny sparks of bioluminescence flashing like underwater stars as microscopic creatures brush past you.
And sometimes there are larger shadows. You sense this massive displacement of water as something gigantic, something ancient and heavy glides silently right overhead.
A predator, like a giant of the sea.
Yeah, it blocks out the faint moonlight for a second. It's a terrifying eclipse. And then it is gone.
And you just keep pulsing, unbothered, peaceful, just moving to a rhythm that has existed since long before the first dinosaur ever walked the earth.
It really is magical.
It is. That weightless, ancient rhythm belongs to the moon jelly. Welcome back to Saltwater Stories, everyone.
We are so glad you're here with us.
Today, we are taking a truly magical ocean journey to uncover the hidden life of an animal that is literally 95% water.
95%. It's wild.
It is. Our mission today is to explore the astonishing survival superpowers, the shape-shifting biology, and the mesmerizing reality of a creature that has mastered the oceans for over 500 million years.
I mean, it is an organism of absolute paradoxes.
Yeah.
It is so physically fragile that a rough, tumbling wave could literally tear its tissues apart.
Right.
But yet, biologically, it is so resilient that it has effortlessly survived 5 global mass extinction events.
5 of them. It completely forces us to rethink what complexity even means in the animal kingdom, you know?
Oh, absolutely.
So, okay, let's unpack this, because when we say moon jelly, I think a lot of us picture that clear, saucer-shaped blob we sometimes see washed up on the sand at the beach.
Yeah, the classic beach blob.
Exactly. But seeing them in their natural environment, in the water, is a completely different experience. They look like they are made of spun glass.
They really do. They have this translucent, saucer-shaped bell. It's usually about the size of a dinner plate, so maybe 10 to 40 centimeters wide.
But the defining feature, the thing that gives them their name, is what is glowing right in the center of that glass umbrella.
Right, those 4 distinct horseshoe-shaped rings.
They are so pretty.
They are. If you are snorkeling and you look down at a moon jelly from above, those rings look exactly like 4 tiny, glowing crescent moons suspended in a watery sky.
And what is wild is that those beautiful, delicate rings are actually its reproductive organs.
Yeah, they're the engine of its survival. And because the animal is transparent, you can clearly see them right through its own skin.
Which is just so cool. But beyond those glowing rings, there is almost nothing else in there.
Basically nothing.
I mean, this is what absolutely blows my mind. We're talking about an animal that thrives globally without any of the biological hardware we consider absolutely essential for life.
Right? It has no bones to give it structure.
No heart to pump fluids.
No blood at all to carry oxygen.
And maybe the most difficult thing to wrap our heads around, no centralized brain to process information or tell it what to do.
None. It is a masterpiece of biological minimalism. When we look at a moon jelly, we are looking at a design that relies on the physical properties of water just as much as its own body.
Right, because the bell itself is incredibly simple, isn't it?
Very simple. It is made of just 3 layers. You have an outer skin called the epidermis.
Okay.
You have an inner skin that lines its rudimentary stomach called the gastrodermis.
Makes sense.
And sandwiched between them is this thick, elastic, highly hydrated, jelly-like layer called the mesogly.
Mesogly. So it is essentially a two-ply tissue system with like a structural hydrogel in the middle.
Exactly. That mesogly makes up the vast majority of its body weight. It acts as a hydrostatic skeleton.
Because water is incompressible, right?
Yes. So trapping all that water in the mesogly gives the jellyfish enough of a rigid structure to push against the ocean currents. And it does it without needing heavy calcium bones.
It's such an elegant solution. It's like an umbrella made of sea glass that somehow knows exactly how to live without a brain to give it instructions.
It really is. But here is where things get really surprising. For hundreds of years, scientists looked at this perfect glass umbrella design and assumed that every single moon jelly around the entire world was the exact same species.
Right, they just gave it one name, didn't they?
Yeah, Aurelia aurita. Because whether someone pulled one out of the freezing, icy fords of northern Europe or a warm coastal bay in California.
Or the tropical waters of Japan.
Exactly. They all looked physically identical. Same clear bell, same 4 moons.
But looks can be super deceiving in nature.
Highly deceiving. When modern genetic sequencing came along, it completely rewrote the textbooks. The moon jelly is what biologists call a cryptic species complex.
A cryptic species complex. I love that term.
It's a great term. When researchers finally started reading the microscopic DNA instruction manuals hidden inside their cells, they realized there isn't just one global moon jelly.
There are up to 28 distinct species hiding in plain sight.
Up to 28. Genetically distinct species that separated from one another millions of years ago.
Wow.
And they have adapted their internal biochemistry to survive in wildly different oceans. So the enzymes of a moon jelly in the freezing North Atlantic are totally different from the ones in the warm Mediterranean Sea.
But they kept the exact same outward appearance.
Yep.
I mean, it's like having 28 different computer operating systems, from Windows to Mac to Linux, but they are all housed inside the exact same plastic monitor.
That's a great way to think about it.
But why wouldn't their bodies change shape over millions of years? You'd think they would adapt differently.
Well, because the physical design, the glass umbrella, is hydrodynamically flawless. Evolution found a shape that interacts perfectly with the physics of water.
And physics doesn't change just because the water gets colder.
Exactly. So nature kept the chassis and just tweaked the engine under the hood.
That is brilliant. But okay, it brings me back to the brain issue. If they don't have a central processor, no brain, how are they experiencing the world?
It's a great question.
Like, if you or I are swimming in the ocean, we rely on a massive central brain taking in data from specific organs. Eyes for light, ears for sound, skin for temperature.
Right.
How does a living bowl of hydrogel know what is going on around it?
It uses a decentralized architecture called a nerve net.
The nerve net.
Yeah, instead of having all its neurons bundled up into a dense brain inside a head, its nervous system is spread out. It's interwoven across its entire body like a microscopic spider web.
Oh, wow.
And the true magic happens at the very edge of its bell, the rim of the umbrella. That rim is lined with incredibly specialized, tiny sensory structures called rhopalia.
Rhopalia. So these are like the data collectors for the nerve net.
Think of them as localized, multi-tool sensor hubs. They're spaced out around the perimeter of the jelly, and each one contains distinct receptors.
What kind of receptors?
Well, they have simple light-sensing organs called ocelli. They can't see high-definition shapes like our eyes can, but they can detect the intensity and angle of light.
So they know instantly if a shadow is passing over them.
Exactly. And they also contain chemoreceptors to detect specific chemical trails or hormones in the water.
And because it is a distributed network, one side of the jellyfish can sense a shadow and immediately trigger the muscles on that specific side to contract.
Yes. It doesn't have to send a signal all the way to a central brain and wait for a response. The reaction is localized and instant.
It operates just like a decentralized computer network.
It really does. But, their interaction with their environment isn't just sensory, it is also highly visual for anyone observing them.
Oh, right. The colors.
Yes. We mentioned they are translucent, but they aren't always perfectly clear glass. Their colors actually shift dynamically depending on their environment.
Depending specifically on their diet.
Right. Exactly. Because they are transparent, they literally take on the colors of whatever they've been eating.
That is so cool. So if a moon jelly has been drifting through a patch of tiny shrimp-like crustaceans, those 4 moons in the center will start to glow with a deep pink or soft lavender color.
Yeah, and if they've been feeding heavily on brine shrimp, the pigments from the shrimp turn the jelly this beautiful sunset orange.
It is like they wear their metabolic data on the outside.
They really do. It's a direct visual indicator of the local food web.
Okay, but this raises a major logistical question for me. We have this brainless, boneless, color-changing glass umbrella.
Right.
We know what it looks like, and we know how its nerve net feels the water. But how does it actually travel?
Movement.
Yeah, because the ocean is massive, and currents can be violently strong.
Right.
How does a creature with no bones, no fins, and no heavy muscle mass manage to cross vast distances without just totally exhausting itself?
Well, that brings us to one of the most astonishing biomechanical discoveries in all of marine physics.
Okay, I'm ready.
The way a moon jelly swims isn't just visually hypnotizing. It is, mathematically, one of the most energetically efficient forms of movement on planet Earth.
Wait, really?
Yes, they systematically outperform almost every other swimming animal, including sleek, highly muscular fish.
Okay, let's pause on that. A gelatinous umbrella is more efficient at swimming than a streamlined, muscular fish.
It is.
But a salmon or a tuna is practically a torpedo designed by nature. How can a jellyfish beat that?
It all comes down to how they manipulate fluid dynamics. When a fish swims, it relies on continuous brute force.
Right, thrashing its tail.
Exactly.
Okay.
It uses dense muscles to thrash from side to side, constantly fighting the resistance of the water. It takes a massive amount of calories to keep those muscles firing continuously.
But the moon jelly does it differently.
Completely differently. It utilizes a highly specialized burst-and-coast method. It has a single layer of transparent muscle fibers called coronal muscles that radiate out from the center of its bell to the edge.
Kind of like the spokes on a bicycle wheel.
That's a perfect image. So when it wants to move, it fires those coronal muscles, pulling the edges of the umbrella inward and squeezing the water out.
Okay, so that contraction is the burst phase. When it sharply squeezes its bell, it forces a ring of water out from underneath it.
Yes, and fluid dynamicists refer to this specific phenomenon as a starting vortex. It is a high-pressure, swirling donut of fluid that shoots backward.
And because of Newton's third law of motion, forcefully expelling that water backward propels the jellyfish forward.
Exactly.
Okay, that part makes intuitive sense to me. It is like squeezing a turkey baster or a water bottle underwater. You squeeze the bulb, the water shoots out one way, and the recoil pushes back against your hand. It's basically jet propulsion.
It is basic jet propulsion. But if that were the whole story, their efficiency would actually be quite poor, because jet propulsion is energetically expensive.
So where does the efficiency come in?
The true genius of the moon jelly happens during the coast phase.
Ah, this is where the elasticity of that middle jelly layer, the mesoglea, comes into play, right?
Precisely. When the jellyfish finishes its muscular squeeze, it completely relaxes its muscles. It stops doing any active work.
Wow, okay.
Now remember that the mesoglea is a highly elastic hydrogel. It stores potential energy during the contraction, much like pulling back a heavy rubber band.
Oh, I see. So when the muscles relax, the elasticity of the jelly automatically snaps the bell back to its original flat shape.
Yes, but wait, think about what happens when it snaps back to its open shape underwater.
It's rapidly increasing the space underneath its bell, which means it creates a negative pressure zone, a vacuum.
Exactly. It creates a localized vacuum beneath the bell, and nature abhors a vacuum.
So the water from the ocean aggressively rushes up into that empty space to fill the void.
Yes, and this rushing water collides and rolls into a second swirling ring, spinning in the opposite direction of the first one. Scientists call this the stopping vortex.
Okay, so a second donut of water swirls up into the bell.
And here is the physical masterstroke. As that second vortex swirls up underneath the jelly to fill the vacuum, the momentum of that rushing water actually pushes against the underside of the bell.
Wait,
It physically shoves the jellyfish forward again.
it gets pushed forward a second time without flexing a single muscle, just from the vacuum pulling water into its own tailwind?
Yes. Biomechanists call this passive energy recapture. The jellyfish is literally using the kinetic energy of the fluid that it already disturbed to get a free ride.
That is incredible. It is not like a fish fighting the water at all. It is more like jumping on a trampoline made of water.
Oh, I like that.
Yeah, like you use your muscles to push down. That is your energy expenditure. But then the tension of the trampoline throws you back up in the air, doing the second half of the work for you completely for free.
That is a brilliant analogy. The elastic recoil of the mesoglea acts exactly like the springs of a trampoline, manipulating the fluid to do the heavy lifting.
Nature is just amazing.
It really is. And because of this trick of physics, catching that secondary wave, moon jellies get an estimated 30% boost in travel distance for absolutely zero extra metabolic cost.
30% for free.
Yep. They are recycling the ocean's momentum. That is the secret to how they can travel for miles, pulsing relentlessly all day and night without exhausting themselves.
Picture that in your mind right now. A peaceful, quiet night out on a coastal bay. The water is glassy, reflecting the silver light of the moon.
Yeah.
And just beneath the surface, there is a smack, which, by the way, is the actual wonderful collective noun for a group of jellyfish.
A smack of jellies.
A smack of moon jellies drifting together, thousands of them, pulsing in complete synchronized silence, riding these invisible swirling rings of pressure, using the ocean's own physics to glide effortlessly through the dark.
It is a deeply beautiful, almost cinematic image.
It is like a ballet choreographed entirely by thermodynamics.
It really is.
Yeah.
But of course, physics alone doesn't sustain biology. Even the most perfectly efficient swimmer in the ocean eventually needs to get some calories.
Right. Traveling makes you hungry, which brings us to a huge mechanical problem.
How do they eat?
Yeah. They can move beautifully, but they don't have eyes that can target specific prey. And they certainly don't have a jaw or teeth to take a bite out of anything.
No jaws at all.
How does a brainless floating umbrella catch its dinner in a dynamic ocean full of fast, evasive prey?
Well, the answer is that the moon jelly doesn't chase its food at all. Active hunting would completely waste all the energy it just saved through its efficient swimming.
So what does it do?
Instead of acting as a predator in the traditional sense, it turns its entire surface area into a floating, living net.
And a very sticky one.
Highly sticky. The moon jelly continually secretes a thin, specialized layer of mucus over the entire outer and inner surface of its bell.
Mucus.
Hey, it works. As it pulses and glides through the water column, it is constantly passively colliding with microscopic marine life. We're talking about zooplankton, tiny little crustaceans called copepods, floating fish eggs.
So it is literally like wrapping yourself head to toe in double-sided tape and just casually walking through a room where someone is blowing popcorn into the air.
Exactly.
You're just waiting for your lunch to stick to your back.
That is exactly the mechanism. It relies entirely on passive collision. But, getting the food stuck to your back is only the first step. You still have to transport those calories to your stomach.
Right. And the moon jelly's mouth is located underneath its bell, right in the center of those 4 glowing reproductive rings.
Right.
So how does the trapped popcorn travel from the sticky tape on the top of its umbrella all the way down and under to its mouth without any hands to grab it?
Through an incredibly complex microscopic conveyor belt.
A conveyor belt?
Yes. The entire surface of the jelly's bell is carpeted in millions of tiny hair-like structures called cilia. And these cilia are constantly beating in a highly coordinated wave-like rhythm. At a cellular level, they are whipping back and forth.
It is like a... But, okay, we also have to address the elephant in the room when it comes to capturing prey. Because jellyfish are infamous worldwide for one specific biological weapon.
Ah, yes, the sting.
The sting. This is where the moon jelly's passive nature hides one of the fastest, most violent mechanical events in the entire animal kingdom.
It really is. The nematocysts.
Okay, we need to get into the mechanics of this because people are understandably terrified of jellyfish stings. But the moon jellies are generally harmless to humans, right?
They're harmless to our thick skin, yes. But to a microscopic copepod, they are a literal nightmare.
I bet.
Along the fringe of their bell, and densely packed on those oral arms, the jelly possesses specialized stinging cells called cnidocytes.
Cnidocytes.
And inside each cnidocyte is a capsule called a nematocyst. Think of it as a microscopic, spring-loaded harpoon gun.
A microscopic harpoon gun.
Yes. Inside the capsule is a tiny, hollow, tightly coiled thread bathed in a complex venom.
So how does it know when to fire if it doesn't have a brain?
It's entirely mechanical and chemical. On the outside of the cell is a tiny trigger hair. When a piece of plankton physically brushes against that trigger, while simultaneously releasing the chemical signature of prey, it sets off an instantaneous reaction.
Like tripping a microscopic tripwire.
Exactly. And the firing mechanism is driven by pure osmotic pressure. When triggered, the cell wall suddenly changes. Water rushes in violently. The pressure inside the capsule builds up to a staggering 150 atmospheres in a fraction of a millisecond.
150 atmospheres. That is like the pressure inside a high-powered scuba tank.
It is.
And then the pressure just forces it to explode outward.
Yes. The sheer pressure forces the cap of the capsule to fly open. The coiled thread inside turns inside out as it shoots forward, extending a sharp, barbed stylet that pierces the shell of the plankton.
Wow.
And the entire firing sequence from trigger to penetration Takes about 700 nanoseconds.
Nanoseconds. That is impossibly fast. It is literally faster than a speeding bullet.
It is one of the most rapid cellular processes ever recorded in nature. And once the stylet penetrates, it injects a neurotoxin to instantly paralyze the plankton.
So it doesn't struggle and damage the fragile cilia conveyor belt.
Exactly.
Okay, but if it is firing these high-pressure, armor-piercing harpoons faster than a bullet, why doesn't it hurt when a human swimmer accidentally brushes against a smack of moon jellies?
It comes down to cellular scale. The harpoons of a moon jelly are incredibly short. They are designed specifically to puncture the thin shell of microscopic crustaceans.
Right.
Human skin is a totally different landscape. The outermost layer of our skin is made of tough, tightly packed, dead keratinized cells.
So to the microscopic harpoon, our dead skin cells might as well be a thick brick wall.
Exactly. When the harpoon fires, it either shatters against the keratin or simply fails to penetrate deep enough to reach any living tissue or pain receptors.
That is so good to know.
I mean, if you have highly sensitive skin, or if they brush against a more delicate area like the inside of your wrist, you might feel a very mild, fleeting tingling. But they physically cannot harm you.
Which is fantastic news for beachgoers everywhere.
Truly.
But unfortunately for the moon jelly, they aren't just the ones eating. They are constantly being eaten. The ocean is full of hungry mouths, and a moon jelly is basically a slow-moving, floating snack.
They really are a highly crucial foundational layer of the marine food web. But because a moon jelly is 95% water, they possess extremely low energy density.
Right, they don't offer a lot of fat or protein per bite.
No, they don't. So predators who rely on them as a primary food source have to consume staggering, almost incomprehensible quantities to meet their metabolic needs.
And we are talking about some of the most massive, majestic giants of the sea, like the leatherback sea turtle, this prehistoric-looking marine reptile that can weigh up to 2,000 pounds.
It's massive.
And it will migrate thousands of miles across open ocean, specifically to hunt jellyfish.
And then there is the ocean sunfish, or the mola mola.
Oh, I love the sunfish. It is arguably the strangest fish on the planet. It looks like a gigantic 1,000-pound swimming pancake.
It really does. And its diet consists heavily of gorging on jellies, not to mention seabirds that plunge from above, and even other larger, more aggressive species of jellyfish that actively hunt their smaller cousins.
So we have to look at the survival mechanics here. If you are a slow, brainless creature, completely lacking heavy armor, and being actively hunted by 1,000-pound giants, how do you avoid being wiped out of existence?
Well, their first defense is obviously their transparency. In the open ocean, there is literally nowhere to hide. There are no coral reefs, no kelp forests, no rocks.
The only way to hide in the open water is to become the water.
Exactly. Being clear makes them nearly invisible from below against the bright surface, and invisible from above against the dark depths.
Camouflage is highly effective, but predators have evolved to spot them anyway.
They have. And a sea turtle taking a bite out of a jelly often won't consume the entire animal. Frequently, a young jelly will survive a glancing attack from a fish, but it will be left missing a huge vital chunk of its bell.
And this is a massive engineering problem, isn't it? We established that they rely on perfectly balanced, symmetrical pulsing to create those vortexes and swim efficiently.
Right.
So if you are missing a quarter of your bell, your hydrodynamics are ruined. If you try to swim with a lopsided umbrella, you won't generate a straight thrust. You'll just spiral helplessly out of control in circles, unable to feed or travel.
Which is why the moon jelly has evolved one of the most mechanically astonishing healing superpowers ever documented. It is a physical tissue remodeling process called symmetrization.
Symmetrization. This completely blew my mind. Walk us through exactly how this works on a cellular level.
Okay, so if a young moon jelly has 8 arms and a fish bites off 2 of them, it does not do what a lizard does when it loses its tail.
It doesn't just grow it back.
No. Generating new tissue requires a lot of metabolic energy, and a wounded jelly is already struggling. Instead of regenerating, it physically reorganizes the existing tissue it has left.
Wait, it just moves its remaining body parts around.
Yes.
But like if a structural suspension bridge loses one of its main support cables, bridge doesn't just automatically slide the other cables around to fill the gap, but the moon jelly does.
Your suspension bridge analogy is actually perfect because the entire process is driven by mechanical tension.
Okay, how so?
The injured jelly continues to fire its coronal muscles, trying to pulse and swim. But because there is a physical gap where the bite was taken, The tension of the muscle contraction is highly uneven.
It is pulling harder on one side than the other.
Exactly. And the jelly cells are highly sensitive to physical forces. Over the course of 12 to 36 hours, the repeated uneven mechanical force of the muscle, pulsing, literally stretches, drags, and pulls the remaining arms around the center axis of the body.
It rearranges its own anatomy based on the physics of its own muscle contractions.
Yes. The cells respond to the uneven tension by remodeling their connections, allowing the tissue to slide until the arms are evenly spaced out again.
That is just, wow. Wait, so if you take a slice out of a pizza, the pizza doesn't just smush itself together to become a perfect smaller circle, but the moon jelly does exactly that.
It becomes a smaller but perfectly balanced circular jellyfish once again.
It heals through movement.
It heals through movement. That is profoundly elegant. It doesn't waste energy trying to replace what was lost. It simply adapts to what it has left, redistributes the load, and finds its balance again.
And that profound cellular plasticity, the ability to completely remodel its tissues based on environmental signals, is the defining hallmark of the moon jelly.
Which perfectly transitions us into looking at how they are born and how they grow.
Mm.
Because if they can remodel their bodies to heal, it makes sense that profound shape-shifting is the core of their entire life cycle.
Oh, absolutely.
And what a life cycle it is. To survive for hundreds of millions of years, the moon jelly has developed a journey that sounds like pure fantasy. It really does. It is a process called metagenesis, an alternation of generations. The jellyfish doesn't just change shape once like a butterfly. It goes through a multi-stage epic.
And it begins with a phase I like to call the explorer.
In biology, this first stage is called the planula. After the adult swimming jellies reproduce, they release these microscopic, oval-shaped larvae into the water column.
The planula?
Yeah, and it looks absolutely nothing like a jellyfish. It is just a tiny, opaque swimming blob, densely covered in those beating cilia hairs we talked about earlier.
And this tiny blob has one singular mission in life. It uses its cilia to swim downward, searching the vast ocean floor for a specific texture.
It's looking for a hard substrate, a rock, an oyster shell, or maybe a submerged pier.
Right, and once it finds that perfect protected spot, it lands, cements itself permanently to the surface, and radically transforms into the settler.
This is the polyp stage. The planula metamorphoses into something that resembles a miniature sea anemone. It develops a narrow stalk attached to the rock and a mouth pointing upward into the water, surrounded by tiny, stinging tentacles.
So it goes from a swimming blob to a stationary, glued-down creature catching passing microscopic food.
And it can remain in this stationary polyp stage for a very long time, sometimes years.
Years.
Yeah. And if the conditions are stable and food is abundant, the polyp will do something strategically brilliant. It will clone itself.
Clone itself.
Yes. Through a process called budding, it will literally grow identical copies of itself out of its own stalk, spreading out to cover the rock in a dense, microscopic forest of identical clones.
It is quietly building an army on the seafloor, but they can't stay polyps forever, right?
No. Eventually, the environmental conditions change. The water temperature drops significantly as winter approaches.
And that cold water acts as a signal for the polyp to begin the most dramatic physical transformation of its life. It becomes the tower.
The strobila. The polyp stalk stretches upward, growing taller. Then it begins to segment itself horizontally. It forms these deep, constricting grooves along the length of its body until it looks exactly like a stack of serrated discs.
Like a stack of tiny, transparent pancakes or a roll of coins.
This segmentation process is called strobilation. But here is where we uncover a truly breathtaking biological secret.
Okay, I love a good secret.
For decades, scientists knew that a drop in temperature was required to trigger this, but temperature alone wasn't enough. In the lab, some polyps would get cold but absolutely refused to strobilate.
So there was a missing trigger.
There was a missing chemical trigger. And it turns out the moon jelly cannot achieve this life cycle on its own. It's completely dependent on its microbiome.
It's microbiome, like our gut bacteria.
Exactly like that. It relies on an invisible community of specific marine bacteria living directly on its tissues. Researchers discovered that if you take a moon jelly polyp, treat it with antibiotics, and place it in a sterile environment without those bacteria, it will never transform.
It will remain a polyp indefinitely.
Indefinitely. Because these specific bacteria produce a highly specific compound, a vitamin called beta-carotene.
Wait, beta-carotene, the exact same pigment that makes carrots orange.
The very same molecule. The jellyfish's tissues absorbed into a powerful signaling molecule called retinoic acid.
Okay.
Now, retinoic acid is famous because it helps direct the development of human embryos. But here, in this brainless invertebrate, it acts as a molecular key.
How does the key work?
The retinoic acid binds to specific receptors inside the jelly cells. When that happens, it unlocks and activates the genes hidden deep within the jellyfish's DNA that initiate the strobilation process.
So without the bacteria providing the raw material, the key is never manufactured, the genes stay locked, and the jellyfish is trapped on the seafloor forever.
Exactly. It is a staggering evolutionary partnership. Two entirely different branches of the tree of life communicating through chemical signals to create the next generation.
Right. Nature is just.
Wow. And once that genetic key is turned and the tower of pancakes is fully formed, we reach the climax of the metamorphosis, the starburst.
It is a spectacular event. Imagine the cold, dark ocean floor at the very end of winter. It is covered in these microscopic, stacked towers. Slowly, starting from the top disk of the stack, the individual segments begin to aggressively pulse.
They wriggle and contract, breaking the connections holding them to the tower, and then, one by one, they pop off.
They launch themselves into the water column.
But they still don't look like adult moon jellies, do they? These newly released baby jellies, the FRA, look completely different.
They look like tiny, 8-pointed stars, like little pulsing snowflakes or starbursts, barely a few millimeters wide, drifting away into the dark ocean. And over the next several weeks, as the FRA eat and ride the currents, the gaps between those 8 points will slowly fill in with new tissue.
Right.
The bell expands and smooths out until they finally mature into the round, translucent grass umbrellas we instantly recognize.
The journey from a swimming blob to a glued-down anemone to a stacked tower to a starburst to a floating moon. It is an absolute masterclass in evolutionary survival.
It really is. But survival in the ocean isn't just about successful reproduction. The ocean is a highly volatile, often hostile environment.
Very hostile.
Sometimes the plankton blooms fail and food runs out. Sometimes the water gets dangerously warm. If you are an organism that relies entirely on drifting with the currents, you can't just migrate to a better neighborhood when things go bad.
No, you can't.
So how does the moon jelly handle extreme, life-threatening stress?
By breaking the fundamental rules of biology.
I love when biology breaks its own rule.
It really does here. They have a suite of survival superpowers that allow them to endure conditions that would wipe out almost any other species.
Superpower number 1, degrowth. What mechanically happens when an adult moon jelly simply cannot find any microscopic popcorn to eat?
Well, if a complex vertebrate, like a fish, runs out of food, it burns through its fat stores, then its muscles, and eventually dies. But when an adult moon jelly faces starvation, it initiates a highly controlled cellular process. It doesn't die, it simply shrinks in reverse.
It shrinks.
Yes. Through programmed cell death, the jellyfish carefully dismantles its own cellular architecture. It absorbs its own tissues, actively reducing its overall mass to drastically lower its metabolic requirements. An adult jelly can shrink down to 1/10 of its original size while remaining perfectly healthy and functional.
1/10 of its size.
Yeah?
Imagine if a human facing a famine didn't just get dangerously thin, but literally shrank down to the size of a toddler to lower their daily caloric needs.
It is wild to think about.
And then the moment a food source returned, they rapidly scaled right back up to normal adult size.
It is an incredibly efficient strategy. They continuously scale their physical body size directly to the available resources of the ocean.
Okay, superpower number 2, the podocyst. What if things get catastrophically bad for the polyps sitting on the bottom of the ocean? Let's say a heat wave strikes.
The polyp deploys the ultimate defensive shield. It dramatically shrinks down, retracts its tentacles, and secretes a hard, heavily armored dome made of chitin over itself.
Chitin, the exact same tough material that crab shells are made of.
Exactly. It completely encases itself in this dome, becoming a podocyst.
Yeah.
Inside this armor, it essentially pauses its biological clock.
It just sleeps.
It can remain dormant in this heavily armored sleeping bag for years, completely ignoring the toxic conditions outside. And when the water chemistry finally returns to favorable conditions, the chitin dome cracks open and the polyp emerges, completely unharmed.
It literally hits pause on its own existence. But the ultimate trick, superpower number 3, is something that defies everything we are taught about the linear nature of life: reverse aging.
Yes, we universally understand the life cycle as a one-way street. You are born, you develop, you mature, you age, and you pass away.
The arrow of time only points forward.
But the moon jelly sees that one-way street and decides to throw it in reverse.
How is that even biologically possible?
Under conditions of extreme physical stress, Perhaps a massive physical injury, or a severe environmental shock, an older ephira, or even a fully mature adult medusa can actually age backwards.
Wow.
It involves a cellular process called transdifferentiation. The adult jelly begins to degenerate. Its bell breaks down, its tissues disintegrate, and the animal sinks to the ocean floor. To an observer, it looks exactly like it is dying.
But it isn't dying.
No.
Yeah.
Once it hits the bottom, the specialized cells of the adult medusa, the muscle cells, the nerve cells, actually reprogram themselves. They revert to a stem-like state and then rebuild themselves into a polyp.
It hits a biological reset button that is like a fully formed butterfly getting stressed by a sudden frost, deciding to dissolve its wings and turn back into a caterpillar.
It is exactly like that. It's real-world Benjamin Button biology. It allows the organism to completely abandon a vulnerable adult form and retreat to its safest, most resilient, stationary life stage.
It is an extraordinary, fail-safe, evolutionary safety net. And, these survival mechanics, the cellular degrowth, the dormant armor, the transdifferentiation, they are so incredibly advanced that it is no wonder they caught the attention of scientists who are looking far beyond the ocean.
Right, let's talk about space.
Yes. Let's trace how this brainless drifter ended up leaving the water entirely and traveling into outer space.
This is one of my absolute favorite stories. In 1991, NASA launched a space shuttle mission carrying the Space Lab Life Sciences 1 module. It was a mission dedicated entirely to studying how biology responds to microgravity.
And alongside the human astronauts, they loaded some very special, unexpected passengers. They sent over 2,400 moon jelly polyps into orbit.
It sounds like a bizarre choice, but the NASA scientists had a very specific, brilliant mechanical reason for choosing the moon jelly. It all goes back to those tiny sensory hubs on the edge of the jelly's bell, the rhopalia.
Right, the multi-tools we talked about earlier that help the decentralized nerve net figure out which way is up.
Exactly. Inside those rhopalia, the moon jelly biologically manufactures tiny, dense crystals made of calcium sulfate. These heavy crystals are called statoliths.
Stateless, okay.
They sit inside microscopic pockets that are lined with highly sensitive hairs. On Earth, gravity constantly pulls those heavy crystals down. As the jellyfish swims and tilts, the crystals roll around and press against different hairs. That physical pressure sends a signal saying, hey, we are tilting 45 degrees to the left.
It is basically a microscopic snow globe inside their rim. On Earth, the snow always falls to the bottom, so the jelly always knows where the ground is, even in pitch black water.
That's a perfect description. But here is the critical connection. Human beings rely on a nearly identical system inside our own inner ears to maintain balance.
We do.
Yes, we have tiny calcium crystals that roll around in fluid-filled canals, brushing against sensitive hairs to tell our brains which way is up. It is our vestibular system.
Oh, I see. So NASA realized that if they wanted to understand how human babies might develop a sense of balance if they were born in a space station, they couldn't exactly send pregnant humans into orbit. But they could send thousands of rapidly developing moon jelly polyps to act as an analog.
Precisely. They wanted to answer a fundamental question. Does biology know how to build a gravity sensor if there is no gravity present during development?
So what actually happened up there in the space lab?
But while orbiting the Earth in microgravity, the astronauts introduced chemicals to trigger the polyps to strobolate. The polyps successfully sliced themselves into towers and transformed into baby jellyfish entirely in a weightless environment.
Wow. And how did they do?
While they were in space, they seemed perfectly fine. They pulsed and swam around. Biology did its job. The jellyfish successfully grew the calcium crystals and the sensitive hairs. But because there was no gravity, the crystals didn't fall to the bottom of the pockets.
In space, the snow and the snow globe just float suspended in the middle.
Yes. But the real scientific revelation happened when the space shuttle returned to Earth.
What happened?
When those thousands of space-borne jellyfish were suddenly subjected to Earth's gravity for the very first time in their lives, the heavy crystals immediately crashed to the bottom of the pockets, pressing intensely against the hairs.
Oh, no. And what happened to the jellies?
They experienced catastrophic vertigo. About 20% of the space-borne jellies were completely incapacitated.
Oh, wow.
Because they had developed their nerve nets in an environment without gravity, their decentralized brains had never learned how to interpret the signals. The physical hardware was there. The crystals in the hairs grew perfectly, but the neural pathways required to process the data had never been calibrated.
They didn't know which way was up because their nervous system didn't know what up meant. They just swam in dizzy, disoriented circles.
Exactly. It was a profound discovery about development. It proved that simply possessing the genetic code to build a sensory organ isn't enough. The physical environment you grow up in actually trains your nervous system how to use that equipment.
Gravity isn't just a force we fight against. It is a fundamental ingredient in how our neural pathways wire themselves.
Right.
That is absolutely wild. From the deep ocean to the vacuum of space, this simple, brainless hydrogel is out there teaching us about our own inner ears.
It really is amazing.
But, let's bring our journey back down from orbit, back to the coastal waters where these jellies truly belong, because lately they've been sending us a very different kind of environmental message, and we need to talk about it.
We absolutely do. We need to zoom out and look at how the moon jelly fits into the grand, interconnected food web of the ocean. And more importantly, what their populations are trying to tell us about how our world is rapidly changing.
Because anyone who lives near a coastline or a harbor has probably noticed this phenomenon in recent years.
Yep.
Sometimes you go to the beach or look over the edge of a marina dock, and the water is just completely choked with them.
Yeah, giant jellyfish blooms.
Massive, sprawling, dense gatherings of moon jellies, sometimes stretching for miles.
Now, to be clear, seasonal blooms are a perfectly natural, ancient part of the moon jelly life cycle. In the spring, when the coastal waters warm up and food becomes wildly abundant, it is normal for billions of those tiny ephrae to pop off their towers and form large smacks.
Right.
However, scientists are observing that these massive swarm events are happening far more frequently, in higher densities, and they're lasting significantly longer than historic baselines.
And it isn't because the jellyfish are suddenly getting smarter or maliciously plotting to take over the coastal waters. It is because human beings are accidentally redesigning the ocean to be a moon jelly utopia.
We are fundamentally altering the marine environment in ways that perfectly cater to every single one of the moon jelly's survival superpowers. There are three primary human-caused factors driving these giant blooms.
Factor number one, real estate.
Exactly. Think back to the polyp stage. That little anemone-like settler requires a hard, relatively protected surface to cement itself so it can begin cloning its army.
And before human industrialization, polyps were largely limited to natural features like rocky reefs or oyster beds.
But look at our coastlines today. We have constructed thousands of miles of concrete seawalls, wooden docks, bridge pilings, breakwaters, and massive offshore drilling platforms.
We have essentially built massive artificial underwater apartment complexes specifically designed to be shaded and protected, which happens to be exactly what polyps prefer.
So they move in, they coat the undersides of our docks, they clone themselves relentlessly for years, and when spring arrives, a single marina can suddenly release tens of millions of jellies into a confined bay.
We drastically increase their required habitat.
We did. And factor number two is overfishing.
Right, because we established earlier that moon jellies feed by passively capturing zooplankton and tiny fish eggs. Well, small schooling forage fish like sardines, anchovies, and herring eat the exact same zooplankton. They are direct ecological competitors.
And commercial human fisheries extract millions of tons of those small forage fish from the ocean every single year. By systematically removing the fish, we are removing the jellyfish's primary competition for calories.
We are leaving an absolute buffet of zooplankton, completely unguarded in the water column.
With unlimited food and zero competition, the jellies grow faster and reproduce more successfully. Plus, we are also heavily overfishing their natural predators, like sea turtles. We remove the ceiling and the floor of their population controls.
And finally, factor number three, which might be the most impactful, nutrient pollution.
Yes. Agricultural fertilizers wash off of our farms, flow down our rivers, and eventually empty into the coastal oceans. These massive influxes of chemicals act like steroids for microscopic marine plants, causing explosive blooms of algae.
And eventually, that algae dies and sinks to the ocean floor, where naturally occurring bacteria begin to decompose it.
And here's the mechanical problem. Those decomposing bacteria consume dissolved oxygen from the water to do their work. They consume so much oxygen that they create a dead zone.
A dead zone.
A region of the ocean with oxygen levels so low that high-energy, fast-moving animals like fish or crabs simply suffocate. If they can't swim away fast enough, they die.
But the moon jelly doesn't have a fast metabolism. It doesn't have a high-energy centralized brain to power or a dense beating heart to supply with oxygen.
No, it requires an incredibly low amount of dissolved oxygen to survive. It can simply absorb whatever trace amounts of oxygen are left directly from the water.
So when an agricultural runoff event turns a vibrant coastal bay into a hypoxic dead zone, the fish either flee or die. but the moon jellies stay.
They survive and they thrive, entirely unopposed in an environment that has become toxic to almost everything else.
So, when we walk out onto a pier and see a massive harbor completely choked with millions of moon jellies pulsing together in the dark, murky water, it is very easy to look at them with frustration, to think of them as an invading army.
But the science shows us that is the wrong perspective entirely. They are not invaders. They are not the bad guys. They are simply doing what their biology has perfectly programmed them to do for over 500 million years,
Adapting.
adapting to the available parameters. They are incredibly opportunistic survivors, and they are merely expanding to fill the massive ecological voids that our activities have created. They're a mirror, reflecting our own environmental impact back at us.
Imagine standing on that dock at midnight. The water is perfectly calm. And below you, illuminated by the amber glow of the harbor lights, are tens of thousands of moon jellies, pulsing slowly. Silent. Beautiful.
They aren't a plague. They are a complex, living indicator of a changing ocean. A biological dashboard warning us of imbalance, but also demonstrating the sheer resilience of life.
They remind us of a fundamental law of ecology. Nature absolutely abhors a vacuum. If we alter the environment and remove the complex species, life will always find a way to fill that void with whatever is rugged enough to survive.
The moon jelly is the ultimate testament to the power of simplicity and endurance.
As we bring today's magical ocean journey to a close, I want to take a second to reflect on how vastly our understanding has shifted over this episode. We started by looking at an animal that seems impossibly, almost laughably simple. No brain, no bones, no blood.
95% water. A creature that is at the complete mercy of the tide.
Yet we discovered an organism that is a master of fluid dynamics, manipulating the physical vacuum of the ocean to swim with unparalleled thermodynamic efficiency.
We discovered a shapeshifter that relies on a chemical alliance with invisible bacteria to unlock its own genetic life cycle. An animal that can physically remodel its tissues to heal, shrink its own body to survive starvation, build a dormant suit of armor, and literally throw its biological clock into reverse when it needs a reset.
An organism that acts as a vital caloric battery for the great giants of the sea, like the massive leatherback turtle and the ocean sunfish.
And a biological marvel that traveled all the way to the stars to help us understand the very nature of gravity in our own inner ears.
The moon jelly is so much more than a translucent blob washed up on the sand. It is a biomechanical masterpiece of survival.
It challenges our deep-seated assumptions about what complex, successful life should look like. It proves that you don't need a heavy skeleton or a massively complex brain to be one of the most enduring organisms on the planet. You just need to be perfectly in tune with the physics of your environment.
Before we go, consider this provocative idea. Engineers and computer scientists are right now studying the moon jelly's decentralized nerve net, that distributed ring of sensors that can react without a central brain, to design decentralized AI networks for deep space probes.
Really?
Yes. They are trying to build machines that can sustain physical damage, reroute their own signals, and keep functioning in the dark without a central processor to guide them.
If a brainless animal from 500 million years ago is providing the architectural blueprint for our autonomous future among the stars, it truly makes you wonder what else we have overlooked.
Exactly. So the next time you look out at the ocean, whether it's a crashing violent surf or a quiet moonlit bay, take a moment to think about the quiet, invisible rhythms happening just beneath the waves,
Think about those glass umbrellas pulsing in the dark.
performing their ancient water dance, perfectly adapted to a world we are only just beginning to understand. What other fragile, beautiful secrets are drifting out there in the dark, waiting to teach us about ourselves?
There is always more to discover, hidden just beneath the surface.
Thank you so much for joining us on this adventure today. Until the next tide rolls in, keep wondering, keep exploring, and we will see you next time on Saltwater Stories.